So today's video is going to be going to go a little more in depth on the fuel injector. My last video I showed the fuel injector waveform, current and voltage, and I'm going to talk a little bit more about that, like why it happens, why there's the inductive spike, and just generally a bit more detail. So let's get started. Before I dive into the injector itself, I want to talk about current flow, or how electricity flows within a circuit. I have a very simple diagram here. So here we have a battery which is producing some type of voltage. It's arbitrary, doesn't matter. We have the positive pole and the negative pole of the battery, and here we have some type of load that is drawing current from the battery. So typically the way you imagine current flowing is it's coming out of the positive, through the wire, through the load, and then back to the negative. And in fact, if we were to use a voltmeter or a amp meter to measure the current, it will indeed be positive in this direction. What I mean by that is that if you were to, for example, to measure voltage with the positive lead here and the negative or black lead here, you would get a positive voltage. If you were to switch these leads around, you would get a negative voltage. On top of that, if you were to measure the current flowing through this system by making a break somewhere here and connecting one end of the amp meter, the positive end of the amp meter here, and the negative end of the amp meter here, so current is forced to flow through the amp meter, you also would get a positive result. So instead of talking about it, or drawing it, let's actually do it. I have here a battery. I also have a very capable volt and multimeter, which does many different things. And I also have here a broken circuit. So what I'm going to do is I'm going to connect this battery. Actually, before that, let's just test the battery itself. So here we have the positive pole of the battery. I'm going to set it to voltage, and we're going to put the red lead on the positive and the black lead on the negative. And we get a positive 8.82. If we were to switch this, we get a negative 8.82. So even our multimeter is telling us that there's something special about this one here, this pole here. The positive pole gives you a positive number, and the negative pole gives you a negative number. We're going to do something similar with amperage as well. This little circuit here just powers up 3 1-watt LEDs when you can connect them. But I'm going to connect them through the amp meter. So I'm going to put it on the milliamp setting. I'm going to make sure to change it. The Fluke 87.5 automatically puts it to AC, so we're going to make sure to put that to DC. And that's it. We're going to put the alligator clips on there. And I'm going to put the red lead on the most positive side of the circuit. So that's going to be this red wire here. So I'm going to clamp that there. And the most negative side of this part of the circuit is going to get the black. The light turns on, and it's drawing approximately 75 milliamps. And if you see, there's no negative, so it's positive 70. Now it's 74 milliamps. If we were to switch these, the LEDs still light up. The LEDs still light up, but if you look, the current is now negative. It was positive before, but it's now negative. So even our multimeter or multimeters seem to show us that there's something special about the positive. It's almost as if the electricity is flowing out of the positive and into the negative, and the multimeter agrees. We'll see the same thing if we were to put an amperage clamp on here too. If we were to put the amperage clamp, if the amperage clamp requires voltage to flow through it from the face towards the back, like I showed in the fuel injector video, you would indeed see positive current in the direction that we measured it, if we were to connect it like this, and you would see negative current if you were to connect it in the opposite way, just like the multimeter. But here's the thing. Here's the secret that a lot of people don't know. That is not the case. Electricity is not flowing from the positive to the negative. It's actually flowing from the negative to the positive. Here I have a little diagram. It's just an example or my own rendering of what the copper atom looks like, since most of the wires we use are copper. This is what I think it looks like. I think Niels Bohr would be rolling in his grave if he saw something like this, but this is going to help for our purposes. Inside the copper atom, the nucleus of the atom, nothing is to scale here, by the way, we would have 29 protons, which are positively charged. We have 35 neutrons, which have absolutely no charge at all. So we're going to put NC for no charge. And we have 29 electrons, which have a negative charge. And the reason I'm showing you this is just to illustrate the fact that the electrons are the ones that have the negative charge, and the electrons are the ones that flow. That's what electricity is. It's literally the flow of the electrons. It's literally the flow of the not particles, but subatomic particles that are in the atom that are flowing between the atoms. So with that in mind, knowing that electric current flow is the flow of negatively charged electrons, and that's all that's flowing, we're going to get to our next point. Here I have the electron flow theory described. These little e's with the negatives next to them represent the electrons. The electrons flow away from the negative poles and towards the positive. Although we were just measuring with the current meter that it seemed like the opposite was true. It seemed like the electricity was coming out of the positive and going to the negative. Well, what's going on here? Well, here I have a little diagram showing what may be going on, or a way of looking at it. I have here a line. If you can imagine that this is a wire, and these are the electrons inside of the wire, and here's the negative post of a battery, and this is the positive post. And we have, for example, here, get a pointer. 6 electrons in a row. Now since they're negatively charged, they want to get away from anything that's negatively charged and go towards the positive side. So this electron here is going to want to go here. So it's going to fill up this gap. I marked the gap as G. I didn't leave an empty space on purpose, and you'll see why. So this electron is going to want to go here because it's attracted to the positive and repelled by the negative. So when that happens, when this electron goes towards the positive, it leaves a gap where it used to be. And now this electron is going to want to go towards the positive as well to fill up this gap. And that's what that looks like. And if we keep going with it, each electron trying to fill up the gap left by the last one, we have a moving gap. And if you look, that gap is moving towards the negative. That is the current that we are measuring with our clamp. The electron flow is going from the negative to the positive, but the gaps between them are going to the negative. That's what we're measuring when we use our amperage clamps, our ammeter, or even our voltmeters. The reason that it shows this as positive and this as negative is that we're measuring the gap. And this is actually done by accident. Benjamin Franklin, when he needed to assign charges, he just arbitrarily chose this is positive and that is negative, and now we're stuck with that. Even though now in the 21st century we know, or we actually learned in the 20th century, way after Benjamin Franklin died, that there were such things as protons, neutrons, atoms, and electrons flow in the opposite way that we were accustomed to. From an engineering perspective, from a mechanics perspective, from an electronics enthusiast perspective, it really doesn't matter much, but this is absolutely necessary to know to understand the waveform of a fuel injector. So now we got that out of the way, I'm going to show you what conventional flow looks like. It's literally gaps moving from the positive to the negative, and I represented gaps as these G's, which kind of look like 9s, but they're G's. G's are the positive going towards the negative, away from the positive, towards the negative. And that's how we're going to look at it now. We're going to look at, instead of looking at it as electrons flowing from the positive to the negative, we're going to look at it as positive gaps going from the positive to the negative. I really hope that makes sense. If that doesn't, please let me know and I will try to clarify it further. So here's the other diagram that I drew. And we're going to look at this part right here now. Here I have something drawn called an inductor. And basically what an inductor is just a coil of wire. I actually have an example of one right here. This is one that I made for another project that I was working on. It's basically just a toroid. Actually, I have many here. It's a toroid, or just a piece of iron that's shaped like a donut. And then I took some magnet wire, and I took it, basically magnet wire is just copper wire with a shellac on it. And I wrapped it around it many times, and now this works as something called an inductor. And what an inductor is a device that allows current to flow through it. But since a wire that is coiled around, especially coiled around a piece of metal, it creates a magnetic field around it. And the magnetic field caused by it slows down the electricity flowing through it. So it's almost as if the electricity flowing through it is almost breaking itself. Now, it doesn't stop it completely, but it does not allow it to increase or even decrease immediately. It takes a small non-zero amount of time. And this is important for understanding how the fuel injector waveform, or why the fuel injector waveform looks the way it looks. Because inside of a fuel injector, there is a coil of wire. That's how they work. There's a coil of wire that becomes an electromagnet, and that electromagnet pulls on a pintle, and that pintle is what is blocking fuel from flowing. When the electromagnet pulls on that pintle, it allows fuel to flow, and that's how a fuel injector works. And of course, there's a spring inside that once electricity stops flowing, the spring forces the pintle back down, and fuel stops flowing. Here I have I guess you want to call it an oversimplified diagram of what's happening with the fuel injector. If we imagine this symbol here as a symbol for an inductor, or you can imagine it as a fuel injector, we can start to understand the fuel injector waveform. So at time equals 0, well, time equals 1, let's say, there is, if we were to assume that this is the Hantek oscilloscope and the orange lead is the positive lead and the blue lead is the negative lead, and we have the negative lead attached to the negative part of the battery, or also known as chassis ground, and we have the positive lead on the negative side of the let me cross this out, I'm sorry, a little confusing there, on the negative side of the fuel injector, and the fuel injector is turned off, it's not getting a ground, you will have 12 volts at this point, because since there is no current flowing and this part of the circuit is attached to the positive post, you will have 12 volts at this point as referenced from ground. So if we start here, we see that the waveform is at 12 volts, and then suddenly it drops to 0 volts. The reason this drops to 0 volts is that this switch now is closed. So it's going to close this switch. Now that the switch is closed, the positive lead of the Hantek is now referenced directly to ground. So there's absolutely no voltage there at all. And it stays like that, until this point here where the switch is suddenly opened. When the switch is suddenly opened, we see a huge spike in voltage. That huge spike in voltage is happening right here, and then it diminishes down, and then it goes back to normal again. The reason this happens is due to the inductance of the fuel injector. If we consider this here to be the fuel injector. When we get to this point here, the current starts to flow through the inductor or through the fuel injector. And it is actually represented by this diagram here. We actually saw it in the other video, but I drew it here. If we were to imagine this is when the switch is closed, current slowly ramps up. It slowly ramps up until it gets to this point here at about 1 amp and then suddenly drops down to almost 0. Not immediately, but there is a slow, gradual, there is a slight ramp to the dropping of the current back down to 0. It's not immediate. There is a slight ramp. Now, if we were to look at this in the context of the fact that the fuel injector is an inductor, it can start to make a little sense. When current starts to build through the injector, a magnetic field starts to form around it. The magnetic field acts to counter the current flow going through the injector, but it doesn't stop it completely. It just slows it down. Once the magnetic field gets to a certain point, or when the computer decides that the injector has been on for long enough, it will shut off current or shut off the ground for the injector, leaving it open here. When that happens, current continues to flow through the injector. It has no choice. This magnetic field that's still around the injector continues to push the current down. Now remember, we were talking before about the electrons flowing from the negative to the positive, the negatively charged electrons going from the negative to the positive, but the positive gaps, so to speak, the gaps aren't real, but we can imagine as if they were real. It still works. The gaps flow from the positive through the inductor or injector to the negative. But when there's nowhere to go, they get backed up. These positive gaps, they build up and they build up and they build up. They have no choice because the inductor or the magnetic field in the inductor or the injector keeps pushing them that way. And they start to build up. And you get a huge positive charge at this point. That huge positive charge is the inductive spike of the injector. That's why you get that. That's also why, if there were to be a short, for example, if we imagine that this is the inductor inside or the coil of wire, if there were to be a short, for example, a huge part of this being melted and it not having to go around but just going straight to this point, the inductance of the injector will go way down. The effectiveness of the injector will go way down, and you won't see this huge spike because there won't be that big of a magnetic field around it. This spike is integral to the health of the injector. It tells you, at least partially, that it is at this point of the circuit, or this part of the injector is healthy. It doesn't tell you much about the pintle or if there's dirt in there, but at least it tells you that this part of the injector is healthy and good. After the charge builds up, it starts to dissipate pretty quickly, and then it goes back down to 0. But now we know why there is this huge spike in current. I drew the rest of this to kind of just show how it looks. If we can, I'll take a few seconds to explain what's going on here. Here we have the battery, and we have the ground here. All these are considered ground. They're all tied to the negative battery post. So here we have the ignition switch, the fuse for the relay, I should probably write that here. Fuel injector relay. Typically the injectors don't have their own relays, but let's just assume it does in this car. So when you turn the ignition switch on, here, just turn that on. The fuse, the current, the positive gaps, flows through the switch, through the fuse, through this coil here, and then to ground. This coil here becomes a magnet, and I really should have drawn the switch going this way, so the switch, it looked like it'll be pulling towards it, but whatever. it'll cause this part of the switch to close, allowing current flow through this part of the relay. So it flows from the positive through the fuse, through the relay, through the injector, out through the coil of wire, which acts like an inductor, out, and then to the PCM or ECU, which through a MOSFET or a switch, an electronic switch that is controlled by a microcontroller, and then that switch gives ground to the injector. This is what's actually doing the controlling. This is this part of the circuit here. So yeah, that's pretty much how it works. If you want more detail about the MOSFETs and the microcontrollers and the grounds, let me know in the comments, and I will do a video specifically addressing how this part of the circuit works. It's actually pretty interesting, but only do it if you guys would like it. So I hope that made sense. If you guys have any questions, please let me know. I love doing videos like this. I had a lot of fun making it, and thanks for watching. Really do appreciate it.